Today I'm going to talk about our NIPS paper, Sample and Computational Efficient Learning Algorithms on the S-Concave distribution. I'm Hongyang Zhang from Carnegie Mellon University, and this is joint work with Nina Balcan. We know that learning algorithms are almost everywhere. Some classical paradigms of learning algorithm include active learning of hard space and learning section of hard spaces. Unfortunately, for active learning of hard space, we cannot get huge improvement on the label complexity if no assumption is made on the underlying distribution. For learning section of hard spaces, the problem is NP high if no assumption is made on the underlying distribution. So to go beyond the worst case, we need to make some nice assumption on the underlying distribution over the instance space. Some existing result first assume that the underlying distribution is a uniform distribution, and later generalize to the log-concave distribution. And in this talk, we want to explore the possibility that whether we can further generalize the distribution. So we want to answer the following question. Can we learn hard space and intersection of hard spaces in polynomial time where the class of underlying distribution goes beyond the log-concave distributions? And the answer is affirmative in this talk. We study a wide class of so-called S-concave distribution for a certain range of S. A distribution is S-concave if its density function to the power S is a concave function. The S-concave distribution includes the log-concave distribution as special case and also go beyond the log-concave distributions, including the Cauchy, the Pareto, and T distribution as special case, which do not belong to the log-concave distribution. We give a series of structural results for the S-concave distribution. We show that the margin of our isotropic S-concave distribution over m arguments is still isotropic, but is S over 1 plus m S-concave distribution. We study the hyperplane disagreements for any two unit vector u and v, and we show that the disagreement between u and v is roughly proportional to the angle between u and v. We also study the probability of band around any unit vector u, and we show that the probability of band is roughly proportional to the bandwidth t. We also study the disagreements outside the margin for any two unit vector u and v, and we show that it can be upbounded by the angle between u and v. With this structural result at hand, we can show that in the Euclidean space of ambient dimension n, for the S-concave distribution for polynomial time and probability at least 1 minus delta, for margin-based active learning, we can get very strong guarantee OPT plus epsilon with label complexity only polylog depend on the 1 over epsilon. Here OPT is the cost of the base optimal classifier, and epsilon can be arbitrarily small. For learning in section of hard spaces, we show that Baum's algorithm succeeds even under the more challenging S-concave distribution. That's all for the talk today. Thank you so much for your listening.